Hi there, Miss Barber here. This lesson is titled Addition and Subtraction Formulas. The objectives of this lesson are 1. Be able to use the addition and subtraction formulas to prove identities and evaluate exact trig values. 2. Be able to evaluate expressions involving inverse trigonometric functions. And 3. Be able to use expressions of the form a sine x plus b cosine x to simplify expressions. Roman numeral 1, addition and subtraction formulas. In this lesson, we continue to add to our list of fundamental trig identities. Here we're going to add the subtraction and addition formulas. Formulas for the sine. The sine of a plus b quantity is equal to sine a cosine b plus cosine A sine B, and the sine of A minus B quantity is equal to sine A cosine B minus cosine A sine B. Now, for the formulas for the cosine. The cosine of A plus B quantity is equal to cosine A cosine B minus sine A sine B, and the cosine of the quantity A minus B is equal to cosine A cosine B plus sine A sine B. Formulas for the tangent. Let's derive them. So we'll start with the tangent of A plus B. We know that this is equal to the sine of A plus B divided by the cosine of A plus B. Now let's expand the sine of A plus B. The sine of A plus B we learned is the sine of A cosine of B plus the sine of B cosine of A. I'm deliberately leaving an extra space there. And the cosine of A plus B is the cosine of A cosine of B minus sine A sine B. Now, to simplify this, I'm going to divide the numerator and the denominator by the term cosine of A cosine of B. So I will write divide cosine of A cosine of B, and divide the second one also by cosine of A cosine of B. Now we're going to separate each of the numerator terms and each of the denominator terms. Okay, let's look at the numerator terms. I'm going to write that as sine A cosine B divided by cosine A cosine B plus sine B cosine A divided by cosine A cosine B. Let's do that for the big denominator. Then we will have cosine A cosine B divided by cosine A cosine B minus sine A sine B divided by cosine A cosine B. Now let's look to see what terms cancel. Cosine B over cosine B becomes 1. Cosine A over cosine A becomes 1. And then in the denominator, cosine A, cosine B, they both cancel. And then let's expand this just a little bit more. So for the numerator, I've got sine A, cosine A, plus sine B, cosine B. And in the denominator, I will have 1 minus, and just so that it's clearly seen, we're going to have sine A cosine A times sine B cosine B. And sine A over cosine A is tangent A. Sine B over cosine B is tangent B. Then we have 1 minus sine A over cosine A is tangent A times sine B over cosine B is tangent B. That is the addition formula for tan of A plus B. Tan of A plus B is equal to tan A plus tan B divided by 1 minus tan A times tan B. And then for the tangent of A minus B, in the numerator, it'll be tan A minus tan B divided by the quantity of 1 plus tan A times tan B. Find the exact value of the following. Part A, sine of pi over 12. In order to find the exact value, we will need to use the appropriate sum or difference formula for each of these trig functions. We will recognize that the sine pi over 12 is the same thing as the sine of, and I'm going to choose pi over 4 minus pi over 6. The reason I picked pi over 4 and pi over 6 is that they have special trig values. Now let's use the difference formula for sine, and we will have that this is equal to the sine of pi over 4 times the cosine of pi over 6 minus the cosine of pi over 4 times the sine, let's make that look like a sine, sine of pi over 6. Now let's put in those exact values. The sine of pi over 4, which we now have memorized, is square root of 2 over 2. The cosine of pi over 6 is the square root of 3 over 2, minus the cosine of pi over 4 is the square root of 2 over 2, and the sine of pi over 6 is 1/2. So now, that's supposed to look like a minus sign. Let's multiply that, and you will have the square root of 6 over 4 minus the square root of 2 over 4. Putting it over one denominator, the exact value is the square root of 6 minus the square root of 2 divided by 4. Part B. Find the cosine of 105 degrees, and we need exact values. So I'm going to look at a sum. I will see the cosine of 105 degrees as the cosine of 60 degrees plus 45 degrees. 60 plus 45 is 105. We know the exact values of the trig functions for 60 and 45 degrees. Now let's use the difference formula for the cosine. So this will be equal to the cosine of 60 degrees times the cosine of 45 degrees minus the sine of 60 degrees times the sine 45 degrees. Now let's replace each of those trig functions with their exact values. The cosine of 60 degrees is 1/2. We'll multiply that to the cosine of 45 degrees, which is square root of 2 over 2, minus the sine of 60 degrees is the square root of 3 over 2, and we'll multiply that to the sine of 45 degrees, which is the square root of 2 over 2. So if we put that together, the first product will be the square root of 2 divided by 4. The second product is the square root of 3 times square root of 2, which is the square root of 6, divided by 4, and putting it over one denominator, the exact value of the cosine of 105 degrees, square root of 2 minus the square root of 6, all divided by 4. Find the exact value of the sine of 13 degrees times the cosine of 32 degrees plus the cosine of 13 degrees times the sine of 32 degrees. We step back for a moment and recognize that this is a sine of a sum of two measurements, and so we can look at this using the addition formula for sines and write that that expression I just said is equal to the sine of 13 degrees plus 32 degrees. And 13 plus 32 is 45, so this will be the sine of 45 degrees, which we know is the square root of 2 over 2. Verify the identity. The sine of the quantity x plus y minus the sine of the quantity x minus y is equal to 2 times cosine x sine y. When proving an identity, you always work from only one side of the equal sign. I'm going to choose to work from the left-hand side because it's got more stuff. I'll start with the sine of x plus y and write that in its expanded form. So I will get sine x cosine y plus cosine x sine y, and then I need to subtract the sine of x minus y. I'm going to put brackets around it just so that I'll remember to distribute the negative. So for the difference, I still have sine x cosine y, but now it's going to be minus cosine x sine y. Let's write that line again, but distributing the negative. So we will have sine x cosine y plus cosine x sine y minus sine x cosine y plus, because remember we're distributing that negative, plus cosine x sine y. And some nice things happen. For one, the sine x cosine y, the first one, and the third one cancel. Now you have cosine x sine y plus cosine x sine y, which means you have 2 of those cosine x sine y. And we were able to transform the left-hand side to match what was on the right-hand side. Evaluate sine of theta plus phi, where sine of theta is equal to 12/13 with theta in the quadrant 2, and tan phi is equal to 3/4 with phi in quadrant 3. So I'm going to begin by looking at the addition sine theta plus phi, and using the addition formula we can expand this as sine theta cosine phi plus sine phi cosine theta. Not real helpful, but let's work with the next sets of information we were given. So we have sine of theta is equal to 12/13, and it's in quadrant 2. So let's draw that triangle. So in quadrant 2, we have this theta. Sine is opposite over hypotenuse, so we've got 12. For the height, 13. Use the Pythagorean theorem to solve for the remaining x distance, and you get actually -5, right? Because you're in the second quadrant. Let's remember that. Now let's go to the other piece of information we're given, and that is tan phi is equal to 3/4, and phi is in quadrant 3, so let's go ahead and sketch our angle in quadrant 3. I'll put the phi. Now, tangent is opposite over adjacent, and so we're going to have, let's see, the opposite would be 3 over the adjacent, and in these quadrants, both of x and y are negative. Using Pythagorean theorem, the hypotenuse is 5. Now, how does that help? We actually get to get the values. So now let's use our triangles to get the exact values. The sine of theta is 12/13. Now we look for the cosine of phi. Cosine is adjacent over hypotenuse, so using the triangle we drew for the tangent, the cosine is going to be the adjacent, which is -4, over the hypotenuse, which is 5, plus sine of phi, and sine is opposite over hypotenuse, so we'll have -3 over 5, and cosine of theta is, let's see, cosine is adjacent over the hypotenuse, so for theta the adjacent is -5 and the hypotenuse is 13. Let's simplify. 12 times -4 is -48. We'll divide that by 13 times 5, which is 65, plus -3 times -5 is +15 over 65. So performing the arithmetic, we got 65 in the denominator, and -48 plus 15 will be negative, let's see, 4 minus 1 is 3, 8 minus 5, okay, -33/65. Roman numeral 2, evaluating expressions involving inverse trigonometric functions. When evaluating expressions involving inverse functions, remember that an expression such as cos inverse of x represents an angle. Write the sine of the quantity sine inverse of x plus cosine inverse of y in terms of x and y only. Step back for a little bit and we see that the given expression could be written as an addition problem with the signs. Now, that still doesn't help a whole lot, but let's make some substitutions. Let's suppose I say let A equal sine inverse of x. Then, taking the inverse of both sides, we would get that sine of A is equal to x. And let's draw a right triangle with these features. So we draw a right triangle. Let's put A in one of the corners. And sine of A is x. And sine is also opposite, which is x over the hypotenuse, which would be 1. Using Pythagorean theorem, we can solve for the length of the adjacent side as the square root of 1 minus x squared. Let's also do that with b. Let's let b take on cosine inverse of y. Then if we take the inverse of both sides, we would get that cosine of b equals y. Now let's draw a right triangle to represent that as well. So put a b in the lesser angle, and cosine is adjacent over hypotenuse, and cosine of b is y. So the adjacent to b will be y. The hypotenuse is 1. And we use the Pythagorean theorem to solve for the length of the opposite side, the side opposite b, and that would be the square root of 1 minus y squared. Now, let's look at the sum formula, the sine of a plus b, and we know that the sine of a plus b is equal to the sine of a cosine of b plus sine of b cosine of a. Now let's replace it with the x and y equivalents. The sine of a is x. We're referring to the triangle. The cosine of b, remember that cosine is adjacent over hypotenuse, is going to be y. Plus, now we look at the triangle that has the b in the corner. We want the sine of that. Sine is opposite over hypotenuse, so the side opposite b is the square root of 1 minus y squared. And let's do the same thing for the cosine of a. So we look at the triangle that has the a in it. Cosine is adjacent over hypotenuse, and the side adjacent to a is the square root of 1 minus x squared. Now we have expressed this in terms of x and y only. Roman numeral 3, expressions of the form a sine x plus b cosine x. We can write expressions of the form a sine x plus b cosine x in terms of single trigonometric function using the addition formula for sine. If a and b are real numbers, then a sine x plus b cosine x is equal to k times the sine of the quantity x plus phi, where k is equal to the square root of a squared plus b squared, and phi satisfies. Cosine phi is equal to a over the square root of a squared plus b squared, and sine phi is equal to b over the square root of a squared plus b squared. Express sine x minus cosine x in terms of sine only. We're going to need to use the addition formula for the sine, and so let's set it up. This is actually 1 sine x plus negative 1 cosine x. I chose to write it this way so it'll fit the form we need of a sine x plus b cosine x. Then we can solve for k. K is the square root of a squared plus b squared. So for this expression, we're going to have a is 1 squared plus b is negative 1 squared. And when we compute that, we'll still end up with the square root of 2. So we're good with the k value. What we need now is to solve for the phi. And we define that the cosine of phi is equal to a divided by k. A is 1. We just solved for k. We got square root of 2. Sine of phi is b divided by k. B is given as negative 1. We solved for k, and that was negative 2. So we have to find phi, that's the measurement, so that the cosine of phi is positive 1 over the square root of 2, or if you rationalized it and you're more used to seeing it as square root of 2 over 2, that's good too. And the sine of phi is negative. So the quadrant in which the cosine is positive and the sine is negative is in the fourth quadrant. And so we can express the phi as minus pi over 4. And the expression we now get, then I'm going to take out a little corner, is that the sine x minus cosine x is the square root of the sine of x minus the phi that we just solved, which would be, well, it's actually x plus, so it's x plus negative pi over 4, which is going to give us x minus pi over 4.